So in this example, we have, according to a study, 30% of U.S. adults have high blood pressure. 15 adults are chosen at random. What is the probability that exactly 8 of them have high blood pressure? So first, let's just take a quick look and notice that this does give us a binomial distribution. So we have 15 repeated trials. So there's a fixed number of trials, that's 15. They are repeated, okay? Each trial can result in success or failure. So either the person has high blood pressure or they do not. So it's there are only two possible outcomes. The probability they have high blood pressure is fixed. It's constant at 30%. And the trials are independent because we are drawing from a large population, and that is the U.S. adults. So this indeed is a binomial distribution. And in this case, X is equal to the number of adults who have high blood pressure out of the 15 that we randomly selected. Okay, and let's just take note that for this binomial distribution, P is 30%, Q is the complement, so it's 1 minus 30% or 70%. There are N equal 15 trials, and X, the number of successes we're interested in, is 8. So remember the binomial probability formula looks something like this. The probability we have X successes is equal to N factorial over X factorial times N minus X factorial. And we multiply that by P to the X times Q to the N minus X. So in our case, this would be 15 factorial for 15 trials, divided by 8 factorial times 15 minus 8 factorial. And remember, this part of the formula gives us the number of different ways we can have 8 successes in 15 trials. This part is going to give us the probability of success for any one of these ways. Any of these ways. So that's 0.3 raised to the 8th power times 0.7 raised to the 15 minus 8, which is 7. So this is our basic formula. I'm going to figure this part out first. And what I would actually recommend doing this using a calculator. However, I want to show you how to do it by hand, or mostly by hand, just once. Okay, so let's just look at the first part. That's 15 factorial over 8 factorial times 7 factorial. And remember that 15 factorial is equal to 15 times 14 times, 13 times, etc., all the way down to times 10 times 9, and then times 8, 7, 6, 5, 4, 3, 2, 1. So I'm just going to write that as 8 factorial because I can see in the denominator I also have 8 factorial. And what I'm going to do is I'm just going to cancel the two 8 factorials. So that's one way to simplify expressions involving large factorials. So that leaves me with 15 times 14 times 13 times 12 times 11 times 10 times 9. And in the denominator, I have 7 times 6 times 5 times 4 times 3 times 2 times 1. And now I'm going to start to cancel. So I can see that I can see a 15 in the numerator and a 5 times 3 in the denominator. I can also see a 7 and a 2 in the denominator. 7 times 2 is 14, so I can cancel the 14 up here. I'm going to rewrite the 10 as a 5 times 2 because I see 6 times 4 in the denominator, that's 24, and then I see a 12 times a 2 in the numerator, that's also 24. So this leaves me with 13 times 11 times 5 times 9, which is equal to 6,435. Okay, and so remember that is only this part, and normally for these large numbers, I would say just use a calculator. They can do factorials. But if you don't have a calculator, you can kind of do it brute force like this. So far my formula gives me 6,435, and I'm going to multiply that by 0.3 raised to the 8th times 0.7 raised to the 7th power. And if I multiply this all out, I get 0.03477, and it's a decimal. And the decimal keeps going. Let me just create some more space down here. And I'm going to round this to, let's say, 4 decimal places. So this is approximately 0.0348, or about 3.48%. So there's about a 3.48% chance that exactly 8 of the 15 randomly selected individuals would have high blood pressure. One other thing I wanted to point out is how we can calculate the expected value of this binomial probability distribution. We don't have to use the formula that we first learned for probability distributions, because we have this sort of a quick formula that we can use, which is n times p. So in that case, it's telling us that the expected value is 4.5 of the individuals would have high blood pressure. So we expect, on average, around 4.5 of the individuals to have high blood pressure out of the 15. So this kind of explains why the probability of us getting exactly 8 individuals with high blood pressure is, there's a pretty low probability, right? Because the expected number of people is a lot lower. It's around 4.5.